In the last video, we were looking at an example where we needed to have 300 customers weekly in order to be able to break even in some business. So we looked at things like we determined that the probability, first of all, the number of customers each week was independent. We'll talk about what that means later on in this particular chapter. But we determined the probability of having at least 300 customers in a given week was 0.45 or 45%, and therefore the probability of having fewer was 55%. Out of 3 weeks, we could have 0 weeks with 300 or more, 1 week with 300 or more, 2 weeks with 300 or more, and 3 weeks with 300 or more. And this bar graph here demonstrates the different probabilities of each of those based on our assumptions. We then took a look at what happens if we follow through with 52 weeks. And we saw it starting to look very symmetric. And that's not an accident. This is a binomial random variable because ultimately it's based on a number of trials where in each trial something occurs with a given probability or doesn't occur with the complements probability. And when you have enough trials, the probability starts to look like what you're seeing in this picture, this kind of bell-shaped curve. And now if we wanted to say, this is out of 52 weeks, if we wanted to calculate something like what's the probability of having 40 or more weeks with at least 300 customers, that gets to be a nuisance because there's a lot of numbers to add up. So we can make this simpler by approximating this distribution with what's called a normal distribution. So this is called the normal approximation, where what you see on the left is approximated by a probability distribution given by this smooth continuous curve called the normal distribution. The normal distribution, normal random variables are continuous random variables. The last random variable, even with 52 weeks, the number of weeks was 0, 1, 2, 3, right? So they're all kind of isolated. Here we could have 5.3, 5.30001, and so on, right? And so that's why this is known as a continuous random variable. Now, we don't get the probability of events from the height on the curve for continuous random variables. We have to use areas under the curve. Well, because the area under the curve at a single point for a single value is infinitely thin, the probability of any individual event, specific event, is 0. But that's not what you look at with continuous random variables. Instead, we look at regions. So, for example, the probability that x is less than some number is given by the shaded region. If you look at this picture, I use c instead of x, but it's the shaded region from negative infinity up to c, and you figure out that area. How do you find that area? Well, we use tables for normal distributions. Let's just look at a few more examples of how you manipulate this. So the probability that the random variable you're interested in falls between some value a and some value b is this region here where a and b are the left and right endpoints. And the way you figure that out is using the tables. You can find the probability that x is less than b. That's this region from all the way to the left up to this point here. And then you subtract off this tail, which is the probability that x is less than a. The reason we have to do that is because the tables only give us probabilities in the form the probability that x is less than the number. So once again, you take the full probability, add the area everywhere to the left, and you subtract off this tail. Since the probability that x falls somewhere is 1, if you want the probability that x is bigger than some value, what we have to do is find the left side probability and subtract from 1. Once more, that's because the probability tables we're going to use only involve probabilities of this form, probability x less than a number. So what about the probability that the number of customers we have, the number of weeks where we have at least 300 customers is 40 or more? And let's say we need that in order to break even after we've made adjustment to our cost structure. Well, there's one more thing we have to be able to do in order to use the tables and the normal approximation to get that probability. And that involves expected value and standard deviation of random variables. which in and of themselves are important and valuable of their own right. We turn to that in the next section.